In this lesson, we'll tackle the question, can understanding the brain make us better learners? The answer is going to be yes, and we should note that this lesson assumes knowledge of system consolidation. Briefly, system consolidation is the post-encoding reorganization of long-term memory over distributed brain circuits. Those two important brain circuits would be the hippocampal system and the cerebral cortex. And the idea is when we learn something, we make a strong hippocampal memory trace, but the cortical memory traces are weak. And the process of system consolidation then strengthens those cortical memory traces so that retrieval of the memory is less dependent upon the hippocampus. And we'll use the metaphor that the hippocampus is sort of teaching the cortex to strengthen long-term memories. We also noted why the brain undergoes this system consolidation. And the idea is that memory traces in the hippocampus are vulnerable to decay in three ways: interference due to new learning, interference due to new neurons, and interference due to synaptic resetting during sleep. So it makes sense then to reorganize memories and to store them in the long-term storage system. That's the cerebral cortex. The hippocampus must remain ready for new learning. And so system consolidation then reorganizes memories to store them in the long-term system, and that allows the hippocampus free to learn new things. So in this part of the lesson then, we're going to follow information as it enters the brain and is stored. The first stage, then, say in a study session, is we're going to encode the information. So our cortex is going to be processing what we're seeing and what we're hearing and what we're feeling. And we'll have an allocation event going on here. A subset of those cortical neurons will be allocated to store a memory trace of that information, that sensory specific aspect of the total learning experience. Well, cortical neurons send signals down into the hippocampus, so we get convergence of that information, and hippocampal neurons, again, will also be allocated. So a subset of hippocampal neurons will be, in a sense, responsible for forming a memory trace that links together the sensory aspects of the learning experience. And this would be the storage, then, phase. We're beginning to set up a memory of the learning event. The hippocampal memory trace is connected to the cortical memory traces, but the hippocampal memory trace is strong in the beginning. Now, this is because hippocampal neurons are very plastic. They can grow strong synapses with one learning episode. And we'll just kind of show this with our little icon. The synapse here, the terminal, has increased significantly in size, indicating that a single learning event can cause lots of plasticity here, lots of LTP, long-term potentiation. And we get a greatly increased synapse strength right here. And here's the phrase that we noted for plasticity: cells that fire together wire together. And this feature of hippocampal neurons, that they can quickly strengthen their synapses, makes the hippocampus a good teacher for the purpose of system consolidation. And so we have encoded and we have stored the information now. Now when we go to sleep, we're going to reactivate those hippocampal memory traces. They will activate the cortical memory traces, and that will allow the cortical memory traces to get stronger and, in fact, be linked together. We call this system consolidation. So this is this interaction between the hippocampus and the cortex. And this occurs during sleep and at other times as well. But an important time when this happens is sleep. And so this is the hippocampus being a teacher. It is instructing the cortex to strengthen the memory traces that were involved in that learning episode. In the cortex, what's happening among those allocated neurons is a growth process. So synapses are strengthening. Neurons that fire together are wired together. Now, notice there is a reverse flow of information during system consolidation. So when we were learning, it was from cortex to hippocampus, but when we're consolidating, it's hippocampus to cortex. And that makes sense if the hippocampus is necessary in order to help the cortex strengthen these memory traces. But another process happens during sleep, and that is that in the hippocampus itself, the synapses between those allocated hippocampal neurons will be weakened. In fact, lots of the hippocampal synapses are weakened, and this is an important process. This is preparing the hippocampus for new learning. Now, so system consolidation strengthened the cortical memory traces, but on the flip side, the hippocampal memory traces have been weakened. And we saw an explanation for this in the concept of synaptic saturation. So as we learn things, we strengthen synapses between allocated hippocampal neurons. Well, there may be some limit to that plasticity, and so these synapses cannot be strengthened anymore for further learning. So there are finite numbers of synapses here, and there's a limit to the plasticity that can occur at these synapses. So you're going to have to reset these synapses in order to achieve new learning. So during sleep, not only does the brain do system consolidation, but it's also going to reset the hippocampal neurons, so weaken them a bit so that they can be strengthened again for new learning the next day. Now, if we just studied one night and then we go to sleep and we wake up the next morning, we may not be successful in retrieving the information we studied. So that's because only one round of consolidation, we are still left with relatively weak cortical memory traces, and we have weakened the hippocampal memory trace during sleep. So we might have poor retrieval after one learning event followed by one night of sleep. And we can think of that as insufficient consolidation, forgetting as a result of insufficient consolidation. Now, the fact that we have poor retrieval after only one study session should motivate us to study a second time. And during that second study session, then, we're going to be encoding and storing information as well. And because the information is the same as we were studying the first time, we're going to be activating those cortical memory traces. Information will converge down into the hippocampus, and we will strengthen synapses among allocated neurons in the hippocampus. Now, there is a question as to whether these hippocampal neurons will be the same neurons that were allocated during the first learning session. And it may well be that a different set of neurons is allocated on the second study session. So here's how that might look. Up here in this brain here, we see the cortical neurons that are allocated, and here we have these particular 3 hippocampal neurons allocated for the first study session. Now, during the second study session, it may well be that lots of the similar cortical neurons are activated, but a different set of hippocampal neurons is allocated to forming the memory trace for that second study session. So here we see, notice these 3 hippocampal neurons down here are different than the original 3 for the first study session. Now, the idea is that we're still sort of activating lots of the same cortical neurons, but we're simply just linking them together in the hippocampus with a different set of hippocampal neurons. And that's okay, because then when the brain undergoes system consolidation, it's just a new teacher that is going to be strengthening the very same cortical memory traces that encode the information that we've been studying on 2 occasions. And of course, after the second study session, we go to sleep and we have our second round of system consolidation. So whether this is the same or a different hippocampal memory trace doesn't matter. It's the teacher, and it's going to strengthen those cortical memory traces. And so now we have strong cortical memory traces linked together, and we're starting to build a long-term memory for the information we learned. And again, between those allocated neurons, what's going on is a strengthening of synapses. And each time we undergo system consolidation, we can strengthen those synapses. We can grow those spines and put more receptors in and strengthen the communication between neurons. So the more consolidation, the greater the growth. Now, cortical neurons are less plastic. And this explains why we need to do multiple rounds of system consolidation. So cortical neurons are less plastic. They grow strong synapses more slowly after multiple learning episodes. So now let's compare the cortical synapses with hippocampal synapses. We said the hippocampus was very good at doing plasticity, strengthening those synapses quickly after one learning event. The cortical synapses seem to require multiple learning episodes. It's as though they grow more slowly. It takes multiple repetitions to really strengthen those synapses. And this is why we often need to study things more than once if we're going to have a long-term memory. But if we do multiple rounds of consolidation, we can set up very strong cortical memory traces, and we'll have good retrieval. And that retrieval will be good even if we go to sleep and wake up the next morning. We'll still have access to that information because we have made strong cortical memory traces. So we want to think of sort of system consolidation. It's kind of competing with the processes that refresh the hippocampus. If we're going to make long-term memories, we've got to do the system consolidation, strengthen those cortical memory traces, because the hippocampal memory traces are going to decay as a result of those three forces. So we've got to have our teacher be ready to go during system consolidation and do the teaching so that the teacher itself, the hippocampus, can be prepared to learn again the next day. And now then let's take a look at the final sort of concept here. The cortical memory traces decay slowly, which allows for long-term retention of the information. So while we covered plasticity, so growth is fast in the hippocampus, but there's also a fast decay in the strength of those synapses. In fact, sleep, one of the purposes, is to weaken hippocampal synapses in preparation for new learning. Whereas while it takes multiple learning episodes to strengthen the cortical memory traces, once they are strengthened, they decay slowly. And this makes cortical synapses a good repository for long-term memories. So we want to think of the fast decay as serving a function to prepare for new learning in the hippocampus, and slow decay in the cortex serving a function to sustain and maintain long-term memories. So since the hippocampus memory traces decay more quickly, they must be refreshed, strengthened by repeated study sessions spaced out in time. Spacing study sessions allows the hippocampal synapses to be weakened in preparation for the next study session that strengthens them again. So we can just think about the general approach to studying. When should we be studying? We want to study when the hippocampal teacher is prepared to learn, which means reduced synapse strength between hippocampal neurons. And this occurs after sleep or a significant delay since the last study session. This will put the hippocampus in a prime position to be ready to learn again.